Thank you. I hope that you can see the slide and also my voice.
Perfect.
So for the determination of the targeted volatile compounds, for the targeted determination of the volatile compounds responsible for aroma, we consider the fit for purpose of this methodology. For example, for the scientific community, it's very important the extraction capacity of the headspace and to obtain the maximum information. But we should not forget also the demand for a simple method, for the simplicity, and also, of course, the demand for a clear definition of the purpose of the method. So we obtained two methodologies. We can even say a protocol with two versions. One version, version A, for SPME GC FID, and the version B for the SPME GC MS. That's it. The difference is the detector, FID and mass spectrometry. And also we produced an additional protocol for building the calibration cubes for 18 selected volatile compounds. You may wonder why keeping two detectors instead of selecting one of them. Well, it's long to explain, but I will say that actually the reason for that is because we wanted to keep the versatility and adaptability of the method by having the two options depending on the availability of your lab, but also because we wanted to know the performance of the two detectors at the end of the project. So that's why all the time we worked with FID mass spectrometry. This slide shows the 18 selected volatile compounds. They were selected because they show significant differences in the concentration in the three categories, extra virgin, virgin, and lampante. And that's why they were selected. But also they were selected because they were responsible for the different sensory defects, and also some of them because they were responsible for positive attributes. So these are some of the materials necessary for the methodology. One important point is to have in the GC instrument a splitless injector with a liner adapted to SPME sampling. In fact, the SPME that we used is the one with the triple composition. It's proven that it is the best for virgin olive oil aroma. And also, concerning the GC column, we observe at the beginning of the project, when comparing the results from different labs, that it is important to keep a length of 60 meter in order to avoid some overlapping and some resolution problems of some peaks. In fact, during the project, we identified the sources of errors and we try to minimize each one of them. One source of error that we identified from the beginning was the quantitation procedure. And that's why we keep attention to this point, the quantification. So we tested different kinds of quantification and we selected the quantification by means of calibration cubes. We observed that this was the most convenient in terms of accuracy and also practicality. But in this case, we needed to simplify the methodology in order to avoid making individual dilutions for each one of the 18 volatile compounds. That will make the procedure very time-consuming. So we designed two standard mixtures of 18 volatile compounds, and the objective was to avoid making so many injections. So in this way, we can obtain the 18 calibration cubes for each one of the volatile compounds with a less number of injections. The composition of each one of the standard mixtures, you can see in the slide, was optimized according to the concentration ranges for each one of them in natural virgin olive oils, but also we consider the possible overlapping of the peaks in the case of high concentrations. So the result was the composition that you can see in the slide. So with these two standard mixtures, we developed a protocol for the preparation of these standard mixtures and also the use. This is an additional protocol that is applicable for FID and also for mass spectrometry. The objective was to avoid any error in the preparation of the calibration curves. So the quantification of the volatile compounds to obtain the concentration value in milligram per kilograms is, as you can see in the slide, it's by means of the comparison of the chromatographic area in the sample corrected by the internal standard in relation with the calibration curves with the chromatographic areas also corrected by the internal standard. This is the quantification as it is explained in the protocol. In addition to this quantification procedure, we tested other two quantification procedures. So we also tested the calibration curves, but in this case, without the correction by the internal standard. And also we tested a third quantification method, in this case using a calibration curve of the internal standard and the analytes. The best one for us, and the one that we selected for the final validation interlab, was the quantification method one. But we kept all the information to keep testing the performance of each one of them. For example, one very useful tool in the method was to develop an Excel file for all the processing of the data. So you enter all the data in the Excel file, and then you obtain the calibration curves, and you obtain the final quantification. In this case, for the interlab validation was for the quantification method one. But as I said before, we have the possibility to reprocess all the data to obtain data from the quantification method two. So actually the three quantification methods were validated within OLEUM validation. These are the labs that participated, the OLEUM partners that participated in this within OLEUM validation, we can call it. This slide, I showed this slide yesterday, but this is only to remind that for the 18 volatile compounds, for the 6 quality parameters, linearity, repeatability, reproducibility, etc., we calculated the values for the 2 detectors and also for the 3 possible quantification methods. So it was interesting to see this. You can see here some results. It's interesting to see that sometimes for some volatile compounds, the quantification method 2 is slightly better in repeatability, but the quantification method 1 is much better in reproducibility. Of course, everything depends on the volatile compounds. It's difficult sometimes to get a general conclusion. But for the question of which is the best quantification method, the answer is always the better recovery, the better repeatability, and the better reproducibility, with a lot of attention to the reproducibility. So we also consider some important aspects in this validation. One of the most important aspects is the concentration, because we wanted to validate with real concentrations that can be found in real virgin olive oils. That's why we worked with 15 volatile compounds that were selected from a larger set of more than 100 in order to have all the possible concentration values that can be found in virgin olive oil for each one of the 18 volatile compounds. This is difficult, but it was a question of analyzing a larger set and then to select representative samples for each one of the volatile compounds. So with this information, we proceeded to the pre-trial and finally the trial proper that was managed by Queen's University of Belfast. So in this case, in the trial proper, it was also important to consider possible changes during the shipping of the sample. They are volatile compounds. So, you know, the question was, are we going to obtain some oxidation of some changes in the volatile profile? This was a question that we needed to answer. So that's why we analyzed the samples before shipping and after shipping from England to obtain what are the differences in the volatile profiles to make sure that everything was performed correctly. So these are some results I received from Paul Brereton this morning. So he was speeding up in the processing. I would like to thank Paul Brereton for speeding the processing of the data. And of course, I would like to thank all the participant labs that provided the values on time. So now I'm happy to share with you some results. Here we have, for example, for the FID, for acetic acid, we have here some values that go from 20 to 30% of relative standard deviation in the case of reproducibility. In this case, we work with 5 samples that actually they were duplicated. So we obtain all these parameters. Other examples are, for example, ethyl acetate. In the case of ethyl acetate, we obtain a value from 8 to 24%. In the case of ethanol, it was from 8 to 53. We have here in the high value for relative standard deviation a clear influence of the low concentration of ethanol in this sample. And finally, in octane, we have a relative standard deviation between 20 and 30%. Of course, all these values can be compared with the values that we obtain within OLEUM validation, but also at the beginning of the project when the protocol were not harmonized and we obtain higher relative standard deviations. So with all these data, the last objective that we carry out was the calculation of the limits and the concentration ranges for each one of the categories, for extra virgin, virgin, and lampante, for each one of the volatile compounds, and for each one of the detectors, FID and mass spectrometry. In this case, it's very important to have reliable quantification data, and that's why we carry out this calculation with an interlab perspective. So we have 60 samples. They are representative samples. We have 5 labs working with FID and mass spectrometry, and we have 6 sensory panels providing the definitive quality classification into the 3 categories. This is just an example for octane. And you see that this is the typical behavior when you organize the concentration values from the lowest to the highest concentration value. This is the typical behavior. So we have to select one limit for each one of the volatiles, for each one of the compounds. So I hope to provide some insight of the methodology, but of course I will be happy later on to answer any question that you may have. Thank you.